Hello everyone, and I welcome you all to this new series started by GRAMOLY on positional astronomy. As far as I'm aware, this is going to be the first series in the subject of astronomy. And why not? Because learning about coordinates is the most basic things which, or the first thing which you do when you study astronomy. And as far as astronomy and astrophysics Olympiads are concerned, this series is quite important for them too. And specifically, this lecture is pretty important for the NSEA or the IOQA Part 1, as it is now being called, because basically you will know the reason for this assertion as I go through the practice problems at the end of the lecture. Okay, so now without any further delay, let's start with this lecture, shall we? Yeah. So basically, let's first go through some basics which you have probably learned in your lower grades. And if you haven't, that's no problem because now we are going to them. Okay. Now consider this sphere as your Earth. Yes, the Earth. Of course, Earth is not exactly a sphere, but for the sake of simplicity, you're considering it as a sphere. So now you can choose any, not any, but actually two diametrically opposite points as the poles. Okay. Now the equator is the line, or the equatorial plane divides the sphere into two congruent hemispheres actually. Okay, this would be the northern hemisphere, this will be the southern hemisphere, of course. Now let's talk about the parallels of latitude and the meridians of longitude, as they are called. So the latitude is basically the coordinate. Let's just draw a diagram here and explain it so that it would be more clear to you. Okay, now suppose an observer is standing here. So the latitude of the observer is the angle made by the line connecting the observer to the center of the earth with the equatorial plane. So, and it is measured in degrees of north. Basically, if this angle is alpha, okay, yeah, I now let me just take it as phi because alpha kind of results for right essentially in my opinion, but it doesn't really matter. Let's just take it as phi. Okay, so suppose it makes an angle of phi and the observer is standing in the northern hemisphere. This is the north, south celestial one. So the coordinate of the observer would be 5 degrees north. That's it. Simple as that. It's standing here, making an angle of phi. In this case, 5 degrees south. Don't know why it got so botchy, but let me just make it a little bit clean like that. Yeah. So now let's talk about the meridians of longitude. Basically, the longitude is measured from a reference point, and the reference point in our case, or the reference, let me say, reference meridian in our case is the prime meridian, which passes through the Greenwich in England. I think that is in London, but I don't really know. If it isn't, you can always correct me in the comments. Okay, so let me just. And the meridian is defined like an arc, not an arc basically. think you can call it an arc just for the sake of simplicity, connecting the north and south poles. Okay. Or let's just call it a great semicircle, shall we? Yeah, that sounds a little bit cooler. So this great semicircle, basically a great circle is a circle which has the diameter, a circle on a sphere essentially, a circle on a sphere which has the diameter same as that of the sphere. Okay. So the great semicircle has the diameter same as that of the sphere. Although I don't know if it's an accepted definition or not. People just call them meridians. Okay, so let's call this the prime meridian. I'm writing it as PM for short. And let's say we rotated it. Let's say we rotated it anti-clockwise by an angle of alpha. Yep. So all the points on this great semicircle or the meridian have a longitude of alpha degrees east. That's it. And if it was rotated clockwise, okay, the anti-clockwise and clockwise, that the convention I'm taking is from the north, is around the north pole, right? Not from the south pole. Like in my top view, I am seeing the north pole. That's it. Now, if you rotate it clockwise by alpha degrees, so then the points on that meridian would simply have their longitude as alpha degree west. That's it. So, suppose the meridian of this observer was gamma. Sorry, actually, the angle was gamma. Then the longitude of this, then the coordinates of this observer would just be pi degrees north, gamma degrees east. Yep, that's it. Okay, so that's it for the basics. Okay, so now we move to the horizontal and equatorial coordinate system, and this is where the chapter actually starts from. So let us define some terms in the horizontal coordinate system. Firstly, the horizontal coordinate system is based around you, the observer. The zenith is the point directly above you, and the nadith is the point directly below you. These points you can say are the poles of the horizontal coordinate system. Now, the this is the horizontal, the horizon, basically plane of the horizon or horizon. I think it's called the horizon. Okay, because horizon is essentially defined as a plane, and it is the plane perpendicular to the point of the observer. For the sake of clarity, I have drawn it here. This is the horizon. Let me just use my this is the horizon. This is the latitude observer. This is the observer. Okay, now the two coordinates used in this system are the altitude and the azimuth. Okay, for the text, so just denoted by H. Let's just see what it is about. Okay, so the altitude is basically the angle made by the star with the horizon, or basically the line connecting the star and the observer with the horizon. We want to go into details. Okay, so the green thingy is the altitude. And now coming to the azimuth, in this diagram, the azimuth is measured from south to west, but generally to define we use it from north to east, sorry, from the north to east. So the azimuth is basically the angle made by the meridian of the star with the meridian of the with the meridian connecting the zenith from the north. Okay, generally, I mean, because you can also define it connecting to the south pole, but generally, so to speak, we define it from north to east. So the angle made by the meridian to the north and the, sorry, if I said north pole before, I didn't mean it. I meant the north direction. Okay. I think this diagram is a bit skewed, but let's just move on to the equatorial coordinate system. Okay, so the first coordinate here is the declination, right, which is denoted by delta. This is declination of the star. It is the angle measured within the plane of the celestial equator, this, and the object, right. The second coordinate is the right ascension, denoted by the and denoted by the letter alpha. It's the angle makes the which is made by the great circle going through the north celestial pole. Okay. And the vernal equinox, we are going to come to discuss about the vernal equinox in just a bit, and with the angle made by the great circle of the object. Okay, and it is defined to be positive towards east, or basically towards the anti-clockwise direction. I hope this much was clear. Let's talk about the ecliptic, and let's talk about vernal equinox or ecliptic in general. Basically, this is my hand-drawn diagram. Yeah. So the right ascension, so the vernal equinox basically is the point where the sun coincides with the or lies on the equator. Basically, the declination of the sun is 0. So you can say this line passes directly through the sun at the point of the vernal equinox. Now, as we move, another thing is that the the poles of the earth make an angle of around 23.5 degree with the plane of the ecliptic, which is the path or the plane in which the earth revolves around the sun. Now, as we move around the sun at the point of the summer solstice, the sun is at its lowest declination. It is known as this summer solstice. I think I'm repeating myself. Okay. So the right ascension at this point is basically 6 hours, because it's measured from this line. This line, and it is around 90 degrees. Now come to the point of the autumnal equinox. Another uh, so to speak 3 months have passed, and again the declination of sun is 0 now, and the right ascension is 12 hours, I think around 100 degrees. then again 270 degrees more. This is, I think, valid if you consider the path or the trajectory of the Earth to be circular, which it is kinda, but not really because it's elliptical. Now come to the point of the winter solstice. The declination now is negative 23.5 degrees, the declination of the sun, and the right ascension is 20 is sorry is right ascension is 18 degrees, and again uh, after 3 months have passed, we come to the point where the declination and right ascension are 0. So basically the declination of the sun rises from the vernal equinox to the summer solstice, then decreases, okay, till it reaches the equinox, then till it reaches the winter solstice, then rises and reaches the equator again at the vernal equinox. Let me just write the dates if I can remember. So this happens in the vernal equinox happens around 20 early 20s of March. This around early 20s of June. This happens around early 20s of September. This happens around early 20s of December. So basically, a fourth of a year of gap between these four events, and the elliptical is sorry, and the um, what what was I saying? Yeah, the elliptic. Sorry, the ecliptic is the path traced by the sun. Let's move to the next part. But before moving on to the next part, let me just uh, you know just give an insight on the ecliptic. As you can see, this is the vernal equinox, part of the vernal equinox. Now the sun is rising in declination, reaches the point of summer solstice. Then this is the point of then it declines in declination and it reaches the point of the autumnal equinox, then further declining in declination, it reaches the point of winter solstice. Then again, it ascends in declination and reaches the vernal equinox. So that is what I wanted to say about the ecliptic. Okay, so now let's get uh, towards some things which requires a little bit of calculation and a little bit of your attention too. Okay, so basically now we look at the projection of the or the horizontal system in projected onto the earth. So this was the celestial equator. Yeah, we draw a line parallel here. This is the north celestial pole. Again, this is north celestial pole, the NCP. Now suppose the max altitude of this star is A max. Okay, I sorry, I already did a star there. Need to write this again. Sorry about that. Okay, so the uh, latitude of the observer, let's assume it's phi. If this is the altitude, let's say A max, then of course it happens at the time of culmination, the which is when the star gets onto the meridian of the observer, or that is the zenith, the NCP and the uh, star are in the same meridian. Okay, so this is the point of culmination. Let's say the declination is sorry, not the declination actually. This was the equator, right? Yeah. So let's just define the declination as we did here, delta, and this would be A max, this would be pi. So this would be 90 minus A max. Okay. Or the zenith distance would be 90 minus 100. Zenith distance is basically the angle made between the zenith or 90 minus altitude, just for the sake of clarity. Okay. This is 90 minus A max. This is delta. This is phi. Now let's just define a couple of things. So this would be 90 minus phi, and if you sum this together, you would get phi plus, sorry, not phi, actually 90 minus phi, and why am I erasing that? Okay, I guess 90 minus phi plus delta plus A max is 180 degrees. So you can write A max as 90 plus phi minus delta. Now let's talk about A min. Suppose the star is located here. So this would be the declination of the star, delta. And since we are mentioning the A min, and since it is a circumpolar star, circumpolar, which means never setting, then of course the A min would occur when we are on the opposite meridian and not on the same meridian. Basically the same great circle though, so it's called the lower culmination of the star, and that was and the A max, which we discussed earlier, was the upper culmination of the star. Okay, so again let's write a couple of things here. We write the altitude of the star, the declination measured from the celestial equator. Where is that? This is the celestial equator. This is the declination. This is the horizon, and this is the altitude of the star. All right. Now This would be the latitude or the angle phi, this. So this would be 90 minus phi. Okay, and this would be, this is phi. This would be, you can write phi plus, and this would be delta minus a. Delta minus a is equal to 90 degrees. I hope it's visible, but just let me use yellow color. This is 90 degrees. So as I wrote here, phi minus a min plus delta is 90 degrees. Now the condition for circumpolarity is basically that a min is greater than 0. That is, the star is visible at all times. So suppose for the limiting condition of circumpolar star, we tend a min to 0. So we basically get delta is, or the declination of the star is 90 minus phi. That's it. If you want to, now here's an exercise for you. Just calculate the same stuff, but for the southern hemisphere, for an observer located in the southern hemisphere. We are now dealing with observer and stars in the northern hemisphere, but now I want you to do it on your own for the southern hemisphere. But it's not much of work, but it would be a good exercise for you. Now let's just take a look at some problems. Here is one from the NAO. The NAO is basically the second stage of the US Astronomy Olympiad program. The first stage is the USA AAO. The second is the NAO. So it says, which of the following stars is circumpolar in Romania, given the coordinates are 44 degree 25 minutes north, 26 degree 6 minutes east. And here are the stars. Now basically, if it's not that hard, it's just pretty easy, that you have to just sum the not actually sum, just as we calculated in the previous section, that for the circumpolarity you need to have a min greater than 0. All right, so which meant that you need to have this, let me scroll down a bit, you need to have the declination greater than 90 minus phi. So now you can calculate the the declination of the stars as they are given. Calculate the 90 minus phi. We know the latitude. It's around 46 degrees or 45 degrees 70. Sorry, 45 degree 35 minutes, I guess. Yep. So you can obviously see that D is the correct option to go with. Now let's move. Okay, so this was one question asked in the IOQA last year. It was like, which of these star is just it was, which of the star is just circumpolar if it makes an angle of 10 degree from the NCP, and you needed to find the latitude of the observer, not which of the star actually, for what latitude, which of the latitude the star is circumpolar if it makes an angle of 10 degree with the NCP. You can see this question if you see the IOQA 2021 part 1 paper. So this is one, and this is another question from that paper, and this requires the knowledge of basically the path of the sun, or the ecliptic, or basically this requires basic geography if you have studied. So the date is let's read the question first. The latitude and longitude of two series A and B are 13 degrees north, 77.6 degrees east, and 27-degree north and 77.6-degree east. So the longitude is basically the same. So it's asking on 15th of December, and it's given and it's asking us to compare the sunrise and sunset times. So what you have to actually know is, as the sun moves, let me just draw a diagram here, although it's not needed, but for the sake of clarity, as I say. Yeah, so as the sun moves upward, that is towards the summer solstice, the days are longer in the northern hemisphere, or the days are shorter in the southern hemisphere, which is basically because if you see, uh, the sun is no longer visible at the south pole. Okay, and it takes like around 2 days for the sun to rise in the south pole, as far as I know, during the times of summer solstice. Okay, now, so as I was saying, that now if we talk about winter solstice, then the sun moves 23.5 degrees below the equator. So the days are longer in the southern hemisphere now, and they are shorter in the northern hemisphere, and which is basically what we had to know in this question. So our 15th of December is around the time of the winter solstice. So the northern we are, the more the days will be shorter. So for A, uh, it's more southern, so the days would be longer here as compared to B. Okay, so for A, the sun will rise later and set earlier in A compared to B. Option C. Okay, now again, this is a question from the IOQ, and you can answer it as soon as we're seeing the answer is 18 hours. If you don't know, you can just rewind and rewind to the point where I was talking about the vernal equinox and solstice and stuff. Now this is another question from the IOK, although it is not exactly from this chapter, but it requires a similar knowledge, so why not? Basically, what you had to know in this question was that the moon revolves around the earth in a period of 27 days or 28 days approx. So let's just draw the sun, moon, and earth system. This is the earth. This is the moon. Just draw its faces. All right. So it's saying the moon makes an angle of 40 degrees at 6 p.m. on a particular day when the sun is about to set. The R angle of the moon at the same time next day is approximately. Okay, so I don't think I have discussed R angles, which is quite weird, but let me just define them now. So basically, the R angle from the horizontal coordinate system. So this is the observer. So basically, the R angle is the angle between the meridian of the observer and the meridian of the object or the star. Or you can also say that the R angle is measure of the time passed where from culmination, because of course this is alpha angle, and as you know that culmination occurs when the uh, object is on the local meridian. Circular definitions. Okay, so as I was saying, so the moon takes around 28 days to completely revolve around the earth. So as the sun, so as we come across this same point of 6 p.m. in time, the moon would actually be shifted by some angle. Okay, let's say the moon was here, so as it says the her angle is 40 degrees. Now you can calculate how much it moves in 28 hours, which is basically 1 over 28. Sorry, in 24 hours, sorry. In 28 days, it moves 360 degrees. So in one day, it moves 360 upon 28 degrees, which is approximately 13 degrees. So your answer is D. That is it. So as you can see, 4 questions in the IUQ were based on the ideas used in this chapter. So as I said in the introduction, that this chapter is pretty important for the IUQ part 1, that is. And in the next lectures, we'll be studying spherical trigonometry and the conversion between the horizontal coordinate system and the equatorial coordinate system. Yeah, that's it. Thank you for watching.